Here is a tiny atomic nucleus. How can these nuclei provide enough energy to supply electrical power to cities as large as Toronto or Montreal? In 1939, scientists discovered that a large nucleus, such as uranium-235, would become unstable when struck by a neutron. This could cause it to split into two nuclei of about the same size and release 2 or 3 neutrons. Nuclear fission was the name eventually given to this process. If we place the reactants on one side of a balance and the products on the other, we will find that the products are always lighter. Clearly, a mass has disappeared in the nuclear reaction. What happens when a mass like this is lost? Einstein's mass-energy equation predicted that a large amount of energy should be released when the mass is converted to kinetic energy of the fission products. The fission of a uranium nucleus releases more neutrons. These in turn can collide with other uranium nuclei. A chain reaction then becomes a definite possibility. What we need now is a contraption that takes advantage of these chain reactions. A contraption which uses fissionable material as fuel and harnesses energy released during nuclear fission for practical, everyday applications. Today, we have those contraptions, nuclear reactors of several designs, which harness nuclear fission throughout the world. Most reactors use uranium-235 as a fuel. It has 92 protons and 143 neutrons. Less than 1% of natural uranium is U-235. More than 99% is uranium-238. Among so many U-238 nuclei, what happens when a lonely U-235 nucleus undergoes fission? A chain reaction is unlikely because many of the neutrons released are gobbled up by the U-238 nuclei to form U-239, an extremely radioactive isotope of uranium. Other neutrons simply escape from the sample because they are traveling too fast to fission another nucleus. Only a slow-moving neutron stands a fairly good chance of initiating fission in a uranium-235 nucleus. A fast neutron speed cannot be reduced through collisions with other uranium nuclei. But if a relatively small mass like a water molecule is present, the water molecule can absorb a large amount of energy from the neutron. The process slows down the neutron. A number of these collisions will reduce a neutron speed until fission is likely to occur. The name moderator is given to a material used to slow down the neutrons. Ordinary water is a good moderator, but it sometimes absorbs neutrons and so removes them from the reaction. Heavy water is a very effective moderator. It contains an isotope of hydrogen called deuterium, which has a proton and a neutron. It slows down the neutrons, but rarely absorbs them. But with slow neutrons, a nuclear reaction can get too much of a good thing. Too many slow neutrons means too many fissions, and too much energy released as heat. A chain reaction that is uncontrolled could produce so much heat that a reactor could literally melt down. A safety feature is necessary. Within the core of the reactor, surrounded by the uranium fuel, control rods can be lowered and raised.